Hello everyone, welcome to the another lecture of chemical bonding class 11. Myself Suman Singh. So in the last class we have discussed about the hybridization, right? So now in today's class we will discuss about the molecular orbital theory, okay? So first question arises that why there is a need of molecular orbital theory. So when we talk about the needs for molecular orbital theory, it directly depends on the limitation of valence bond theory. Because of the limitations of valence bond theory, the need was arises to generate a new type of orbital theory, which is called molecular orbital theory, right? So first of all, we will see what was the limitations of valence bond theory. So the first limitations was this theory, when we talk about the valence bond theory, this theory was unable to explain the formation of a coordinate covalent bond in which both the electrons forming the bond came from the one atom only. Okay. Now, next one is this theory, valence bond theory, failed to explain. This theory offers no explanation for the paramagnetic nature of oxygen molecules. This was the second drawback of valence bond theory. Now, one more we can see. This theory was unable to provide a satisfactory explanation to the bonding in metals, okay, and odd electron molecules and interstitial compounds. So this was some of the drawbacks of the valence bond theory. That is why there was a need was felt to discover a new type of orbital theory, which is called molecular orbital theory. So when we talk about the molecular orbital theory, it was put forward by Hunds and Millikan in 1932, or we can say molecular orbital theory actually was developed by Robert Mulligan in 1932, and this is supposed to be the most versatile theory to explain the nature of covalent bond. Okay, so what were the silent features of this molecular orbital theory? So the first one is, it has been told here that we will see the first overview. After that I will tell you. So according to the valence bond theory, according to the valence bond theory, suppose this is an s orbit and this is also an s orbit. These two will combine like this, right? According to the valence bond theory, and the electron density was here, right? But according to molecular orbital theory, MOT, when this s orbit and when this orbit s orbit will combine, they will combine like this, okay, and there will be positive charge, here will be positive charge, and electrons were free to move anywhere within this area, right? But according to this molecular valence bond theory, there was electrons can rotate, or we can move in this area only, right? But according to molecular orbital theory, the electrons can move anywhere in this place. So this was the first theory. Now first silent features. Now next one is atomic orbital. We used to represent with what? S, P, D and F, right? But molecular orbital we will represent with sigma, sigma star, okay, pi and pi star, okay. Now next one is atomic. When we talk about the atomic orbitals were monocentric, means one nucleus only, okay. But when we talk about the molecular orbital, they are called polycentric, okay, POLYCENTRIC, okay, polycentric. Now next one is, when to always remember that when two atomic orbital, AO means atomic orbital, when we are in heading two atomic orbital, when they two will combine, they will form two type of orbitals. One will be anti-bonding molecular orbital, and one will be bonding molecular orbital, okay. So anti-bonding molecular orbital is denoted by sigma star and pi star, okay, and whereas bonding molecular orbital is represented by sigma and pi, okay. So always remember that number of number of atomic orbital fused will be equal to number of molecular orbital formed. Okay, so this was the overview. Now we will see in detail. So first of all, what we can say, when two atom approaches each other, what will happen? Their atomic orbital loses its identity and mutually overlap to form what? New orbital called molecular orbital, right? In the same way what I have explained you, suppose this is one suppose this is one atomic orbital, another one, they will combine to form another set of atomic orbital like this, right? Molecular orbital. Now molecular orbitals are associated with the molecules as a whole and are quite quantized. Okay, atomic, when we talk about the molecular orbitals are associated with the molecules, right? Now next one is the molecular orbital are polycentric, as I have already told you. Okay, and they surround the nucleus of the combining atom, and the electrons are considered moving over a whole nuclear system instead of moving around a particular nucleus. I hope you have understood this. Means what he has to tell, I mean to say that they are polycentric, right? And electrons are free to move anywhere in the nucleus within this region. Okay, anywhere within this region. Now next is molecular orbital are formed only by those atomic orbital which are which are of comparable energies. Okay, and process proper orientation, right? Now next, what we can say when we talk about the molecular orbital theory, we can say that the number of molecular orbital formed is same as the number of combining atomic orbital. What I have told you, number of atomic orbital fused will be equal to number of molecular orbital formed. Okay, now next one is what we can say, a molecular orbital can accommodate a maximum of how many electron? 2 electrons. Okay, a molecular orbital can accommodate maximum of 2 electrons. Now in the last, what we can say, that the molecular orbital are filled within a framework of the same rule as applied for the filling of the atomic orbital by Pauli exclusive principle. The system will be same, right? And according to the Hund's rule and Avogadro principle, whatever the filling of orbital, when we talk about the molecular orbital, so when the molecular orbital are filled with the framework of the same rule as applied for the filling of atomic orbital, there will be no change in the filling the atomic orbital as it was suggested by Pauling, Holmes and Avogadro principle. According to their principles, we will fill the molecular orbital also. Okay, now when we talk about the shape of the molecular orbital will depend upon the shape of the combining atomic orbital. Means if it will directly depend on the shape of the combining atomic orbital. Now when we talk about the molecular orbital theory, this molecular orbital theory has been found to be very versatile tools in explaining the nature of the bonding in a large number of molecules. Okay. Now, more striking features of this theory is the concept of molecular orbital, which holds the nucleus of the combining atom together. The most striking features, when we talk about the most striking features of this molecular orbital theory, the most striking features is the concept of molecular orbital, which holds the nucleus of the combining atom together. Now, now we will see, first of all, we will see the difference between atomic orbital and molecular orbital. After that, we will further go into the account of the formation of molecular orbital. So here it is directly given the formation of, I think, let me see here if it is given. Yes, difference between molecular orbital and bonding molecular orbital. No. So we will see first what is the difference between molecular orbital and antibonding molecular orbital. Atomic orbital and molecular orbital. So what is the main difference? So when we talk about the atomic orbital, atomic orbital and molecular orbital. So when we talk about the atomic orbital, in atomic orbital, the electron cloud is associated to the nucleus of a single atom, and the atom is called what? Monocentric, right? Now, but in the case of molecular orbital, in a molecular orbital, the electron cloud is associated with the molecules as a whole and is spread over the whole nuclear system of the combining atom, right? And it is also a polycentric, right? Now, next is when we talk about the atomic orbital, they are pure orbital and are obtained by solving the Schrodinger wave equation for the given atomic system, right? So we have discussed the Schrodinger wave equation in atomic structure, right? So this when we talk about the atomic orbital, they are obtained by the solving the Schrodinger wave equation. But when we talk about the molecular orbital, they are usually obtained by the combination of atomic orbital of the combining atom. Okay. Now in the last, what we can say, this atomic orbital possess high energy and are less stable, but whereas the molecular orbital, when the bonding molecular orbital possess lesser energy and are more stable. Okay. So I hope you have got some idea about the molecular orbital theory, right? Now next we will see the formation of molecular orbital theory. So when we talk about the formation of molecular orbital theory, there will be two type. Okay, so we will see here there are various methods of approximating the correct molecular orbital. Among this, we will see the two, which one is LACO, one is LCAO, okay, and another is UA method and LOCA method. So LCAO is what? It is a linear combination of atomic orbital method, okay, which is called LCAO, linear combination of atomic orbital methods. So first of all, we will see LOCA. Okay. So when we talk about the LOCA, see, so this is called linear combination of atomic orbital. So in a linear combination of molecular orbital method, the correct molecular orbitals are approximated by combining linearly the atomic orbital of the atom that forms a molecule. Okay, so what is the how we will see the linear combination? So we will see like this: when two combining atom approaches each other, what happened at that time? Their atomic orbital of comparable energies combine to form molecular orbital, right? So when two orbital approaches each other, at that time what will happen? Their atomic orbital of comparable energies combine to form what? Molecular orbital, right? Like this, like this. So at that time, during this process, during the process of this during this process, there can be two possibilities. Okay, during this process, when these two atomic orbital approaches each other, at that time there will be a two possibilities. So what are the two possibilities? So the first possibility is like this: the first possibilities may be like this one is suppose plus, this one is minus, and one more here, this one is plus, this one is minus. Okay, minus plus. So the first possibilities may be, if the electron wave of the combining atom, this is the electron wave of one combining atom, is there another one, right? So if the electron wave of the combining atom reinforce each other, means what? The crest of one wave overlap the crest of other wave, Okay, an attractive molecular orbital of low energy is formed, which is called bonding molecular orbital. Means what? This is what is crest and trough, right? One is crest and another one is trough, right? There is crest and another one is trough. If the crest of this and the crest of this combined, when they will come across each other, when they will, if they will, the crest of each and the trough of each this and the trough of this, when they will reinforce each other, when they will combine with each other, means crest and trough when combined with each other, at that time the attractive molecular orbital which will formed here, the attractive molecular orbital which will formed here like this, the attractive molecular orbital which will formed here, okay, which can be represented as psi a plus psi b. The attractive molecular orbital of low energy is formed, and this type of orbital is called bonding molecular orbital. Okay, when the crest and trough of the electron wave combines, means the crest of this and the crest of this will combine, and the trough of this will combine. At that time, the attractive molecular orbital which will form will have a low energy. Okay, low energy, and this type of bonding orbital is called what? Bonding molecular orbital. Okay, now next criteria is, the next possibilities is that the if the electron wave of the combining atom opposes each other, means what? Let me draw here. One is this, one is this like this, another one is this like this. Suppose in the second case, what will happen? If the electron wave of the combining atom, these two combining atom, opposes each other, means what? The crest of this met with the trough of this, and the trough of this meets with the crest of this, right? Means what? The crest of one wave overlap through the through of the trough of the other. At that time, what will happen? At that time, the repulsive molecular orbital of higher energy will develop. Okay, at that time, a repulsive molecular orbital of higher energy will develop, because it will cancel out, like this will, it will become like this, right? It will, because they are cancelling each other. So at that time, what will happen? A repulsive molecular orbital of higher energy is obtained, and this is called what? Anti-bonding molecular orbital, right? So I hope you have got the idea of a bonding molecular orbital and anti-bonding molecular orbital. What I have told you, this linear combination of atomic orbitals, they used to proceed in two forms. What we have said, what we have seen, that when two combining atom approaches each other, the atomic orbital of comparable energy combine to form what? Molecular orbital, right? So during this process, there should be two possibilities. If the trough meet each other, then it will be bonding molecular orbital. And the second one, if the crust and trough meet each other and the trough and crust meet each other, at that time they will form anti-bonding molecular orbital, right? So I hope you have understood this. As you can see, it is given here also. As you can see, when the crust of one meeting the crust of one, at that time they are forming when bonding molecular orbital. But at the same time, when the one trough and one crust is meeting, at that time they are forming anti-bonding molecular orbital, right? So as you can see here, now one by one we will see what is bonding molecular orbital and what is anti-bonding molecular orbital, right? So now when we talk about the bonding molecular orbital, so we have seen that the bonding molecular orbital is a bonding molecular orbital is formed when the electron wave of the combining atom are in the phase, that is, both have a positive amplitude, right? So in this molecular orbital, what will happen? The electron density is centered between the nuclei of the combining atom. Okay, at that time, what will happen? The electron density is centered between the nuclei of the combining atom, right? Now what will happen after that, it will shield the two nuclei from the mutual repulsion and hold them in a definite distance, which is equal to the bond length. Now, okay, now due to the increase in the attraction between the two atoms, what will happen at that time, the energy of the system will decrease. Okay, so that is why we have seen that the bonding molecular orbital is a low energy orbital, right? So we will see here, according to this LCAO, what we have seen here, which is a linear combination of atomic orbital method. So according to this method, the wave function, when we talk about the wave function of the molecular orbital, there can be obtained uh, by adding the wave function of the combining atom. Okay, according to LCAO method, the wave function of the bonding molecular orbital can be obtained by adding the wave function of the combining atom. Okay, so let us take the example of H2 molecules. Okay, so when we take the example of H2 molecules, at that time, let say psi 1 and psi b are the wave function of the two identical hydrogen atom A and B. Suppose we have two hydrogen atom, one is A and another one is B, and their wave function is psi A and psi B, right? So at that time, they are represented in a wave like this. We can represent them in a wave like this. We can represent, if you want to represent them, suppose this is here A, this is A, and this is B here. Suppose this is B here, sorry, so this is B here. So it can be represented like this. It can be represented like this. Let me take the line here. It may be represented like this. Okay, it will go here, and one will start from here, it will go here, right? So this is plus and this is minus, so it can be represented like this. Now when we talk about the wave function of psi b of the bonding molecular orbital, when we talk about the wave function of the bonding molecular orbital, suppose it is noted by psi b, right? So what will be the wave function? The wave function will be psi a plus psi b, right? So I hope you are understanding this, right? Now the wave function, which is this one, of the bonding molecular orbital, can be shown like this. This is one line here, sorry, one line here, and this can be shown like this. Okay, here will be B, here is A, this is A, sorry, this is A, and this is B. This can be represented like this, right? Now when we talk about the charge density in the molecular orbital obtained, can be obtained by a squaring. Okay, when we talk about the charge density, so it can be obtained by squaring like this. You can obtain like this, which is psi b square, which is equal to psi a square plus psi b square plus 2 psi a and psi b, right? So this was about the. Now next, what we can say, since this psi square, when we talk about this psi square, represent what? Charge density, right? And when we talk about the psi a square and psi b square, it represents the charge density of the isolated atoms, right? But when we talk about this psi b square, what does it represent? It represents the charge density of the bonding molecular orbital, right? So what we can say, the charge density between the two atoms bonded in a molecule, okay, bonded in a molecule, as we have shown in the previously in the diagram. So what we can say, the charge density between the two atomic between the two atoms bonded in a molecule, which is a psi b square, as shown here. It's shown like this, it can be shown like this, right? It can be shown like this, okay. This should be, here should be b and here should be a, okay, shown like this. The strength, when we talk about the strength of the bond between bond will depend upon the value of this psi b, okay. When we talk about the strength will depend on this psi b. So what we can say, if we are increasing the value of psi b, greater will be the charge density between the two nuclei and stronger will be the bond between them, right? So what we can say, higher the value of this psi b square, greater will be the charge density between the two nuclei and stronger is the bond between them, right? So now from it is clear that the charge density of the molecular orbital, which is this psi b square, is greater than the sum of the charge density of the two isolated atoms, which is psi a square and psi a square plus psi b square, right? From here we can easily identify that the density, the charge density of the molecular orbital, which is psi b square, is greater than the sum of the charge density of the two isolated atoms, which is psi a square and psi b square, by a term which is 2 psi a and psi b, right? So what we can say, this term can into an exercise, or we can say this terms come into existence due to the overlap of atomic orbital, right? So therefore what we can say, the stability of the bond will depend upon the extent of overlapping, okay. At last what we can say about the bonding molecular orbital, larger the overlap, greater is the charge density between the nuclei and more stable is the bond, right? So I hope you have understood the bonding molecular orbital, right? Now we will see anti-bonding molecular orbital, right? We will see, everything is written here, you can, if you will read, you will find this thing, everything is here. So now next is when we talk about the anti-bonding molecular orbital. So when we talk about the anti-bonding molecular orbital, it is formed when the electron wave of the combining atom are not in a phase, right? One means what, one possesses a positive amplitude while the other possesses a negative amplitude. So in this case, the wave function of the component atoms cancel each other, okay, and form a node between the nuclei. What will happen at that time, since the wave function of this component are cancelling each other, so what they will form, they will form a node between the nuclei, okay. In such an orbital, when we talk about this, I hope you are understanding this, because what we have seen, the combining atom were not in the phase, means one crust was combining with the one trough and one trough was combining with the crust, right? So that is why in this case what will happen, the wave function of the component atom will cancel each other, okay, and form a node between the nuclei. So in such case, and at an orbital electrons, in such case, if you will see that the electrons are in those region of the space where they are not under the attraction of both the nuclei, right? And there, in such case, we have seen that the atoms, or we can say that the electrons are in those regions in the space where they are not under the attraction of both the nuclei. Right now, if we see the possibility of finding the electrons between the nuclei, when you will see the possibility of finding the electron between the nuclei, it is negligible, approximately negligible, right? So because the two nuclei repel each other and make the molecule unstable, that is why, because these two nuclei will repel each other and hello, hello. So now, so thus what we can say, the nuclei to two nuclei repel each other and make the molecule unstable. Now, each electron in anti-bonding molecular orbital, what it will do, it will contribute to the repulsion, okay, and it will increase the energy of the system. So thus what we can say, and thus we can say that an anti-bonding molecular orbital is a repulsive orbital of higher energy. Okay, now the same example what we have taken before for bonding molecular orbital, we will say take here. So according to this LCAO, right, according to this LCAO, the wave function, which is for antibonding, we are taking as here as psi a. Okay, so the wave function psi a for an antibonding molecular orbital can be approximated by substituting the wave function of the individual atom, right? So if we are taking psi a and psi b, okay, if you are taking psi a and psi b and represent the, it will if it is representing the wave function of the two isolated hydrogen atom, then for psi a we can represent like this: psi a is equal psi a minus psi b. Okay, now here the wave function psi a for an antibonding molecular orbital, we will show here, it is shown like this. The wave function psi a for anti-bonding molecular orbital can be shown like this. One will go here and it will come here like this. This will be b and this will be a. Okay, and this like this line will be there. Okay, this is plus and this is minus. This can be shown like this, but the charge density, which is psi a square, it is in an antibonding molecular orbital, can can be obtained by squaring, right? Like this, it will be, it can be shown like this. Mm, as you can see, by squaring, and by we can obtain by squaring just like this, just like this. Psi, sorry, psi a square plus psi b square minus 2 psi a psi b, you can represent like this. Now from the above equation, it is clear that the charge density, from this equation it became clear that the charge density of an antibonding molecular orbital, which is this one, is less than the sum of the charge density of the two isolated atom, which is psi a square, psi a square plus psi b square. Okay, which is what we can say, which is less than the sum of the charge density of these two isolated atoms by the term of which one, by the term of 2 psi a and psi b, right? So I hope you are understanding this. So this implies that the charge density between the combining atom in a molecular orbital is less than it would be between the uncombined atom. Okay, now the energy, when we talk about the energy of the of this molecular orbital, it will be greater than the sum of the energy of the component atom, which is a and b. The and the resulting bond which we will form here will be less stable. Okay, now if we are taking the charge density psi a square of the anti-bending molecular orbital, as it is shown, if it is shown like this, as you can see, which is shown like this. This is suppose B, this is A, and this is C. So it's shown in here. The point A and B represent two nuclei. Okay, here this point A and point B. Here these 2 points represent the nuclei. And from this figure, it will become clear that the antibonding orbital decreases the electron density between the nuclei. As you can see, decreases the electron density between the two nuclei. As you can see the curve, right? It is decreasing. Now curve X, a curve on an x-axis. When I talk about the curve on an x-axis, curve on an x-axis at a point C, here, and between this A and B, the point C is what? It is a nodal plane. Nodal plane means what? Where the density of finding an electron is all approximately zero, right? Or the density of finding an electron is zero, and this implies that the probability of finding an electron between the nuclei is almost zero, as you can see, because this is just touching the line, right? So it means that it is a nodal plane. It is touching the nodal plane now, and here the density of finding an electron is almost zero. Again, the nuclei, when we talk about the nuclei does what it will do, what they will do, they will repel each other and it will destabilize the molecule. Okay, these two nuclei will repel each other and they will destabilize the molecule. So I hope you have understood what is bonding molecular orbital and anti-bonding molecular orbital. So we will show the difference between bonding molecular orbital and anti-bonding molecular orbital. So the first difference is a bonding molecular orbital. When we talk about the bonding molecular orbital, a bonding molecular orbital is formed when electron wave of the combining atom are in a phase, that is, the lobe of the atomic orbital have the same sign, right? That's what we have seen. But when we, in the case of anti-bonding molecular orbital, it is formed when the electron wave of the combining atom are not in the phase, that is, the lobe of the atomic orbital has the opposite sign, right? Now next, what we can say, the wave function of the bonding molecular orbital may be approximately by summing the wave function of the combining atom, which was psi b is equal to psi a plus psi b, right? Which was psi b, psi b is equal to what? Psi a plus psi b, right? But in the case of anti-bonding molecular orbital, the molecular orbital is obtained by subtracting the wave function of the combining atom, which was psi a, which was psi a minus psi b, right? Like this. Now the electron density is centered between the nuclei of the combining atom, as we have seen. But in case of atomic anti-bonding molecular orbital, the probability of finding an electron between the nuclei of the combining atom is negligible, as you have seen, we have seen in the diagram, right, just now. Now again, the energy of the bonding molecular orbital is less than the atomic orbital of the combining atom, right? But when we talk about the anti-bonding molecular orbital, the energy of the anti-bonding molecular orbital is greater than the atomic orbital of the combining atom, right? Now next, the last point, what we can conclude here, that electron present in the bonding molecular orbital leads to the attraction between the atoms and stabilizes the molecules. But when we talk about the anti-bonding molecular orbital, the electron present in the anti-bonding molecular orbital leads to the repulsion between the atoms and destabilize the molecules. So I hope you have understood what is bonding molecular orbital and what is anti-bonding molecular orbital, right? So now in the next class we will see the combination conditions for the combination of atomic orbital, or we can say that the formation of uh, molecular orbital. Okay, and we will see energy of the molecular orbital, or how to draw the molecular orbital diagram. We will see this. Okay, so I hope today's class you have understood, so keep up to this. Now in the next class we will discuss the how to draw molecular orbital diagram. Okay, and till that, thank you.